All right, hi guys. We are looking at the next piece of our special segments and triangles. Last time we reviewed medians and the centroids. We've already looked at perpendicular bisectors and the circumcenter, and then angle bisectors in the incenter. So we have one more to look at today, and that is our altitude. So specifically, an altitude of a triangle is the segment that is from a vertex to the opposite side of the triangle. So that's a big clue here. It has to come from a vertex to the opposite side of a triangle, and it's got to do it at a right angle. And again, you're looking for that 90 degrees. So it has to connect a vertex to a 90-degree angle. So that's what it needs to look like. So that altitudes are perpendicular to the sides of a triangle. Now that doesn't mean they're perpendicular bisectors. They're just perpendicular. So again, they go from a vertex to the right angle. So we can have three kinds of altitudes here. An altitude can be inside the triangle. It can be outside the triangle. Or it can be on one of the sides of a triangle. So it depends on what kind of triangle classification do we have. So let's look at this first triangle that we have here. All right, specifically, this is an acute triangle. All my angles would be less than 90. So if I was to draw an altitude for this, let's say we start at this bottom section, I need to draw a right angle from that vertex to the opposite side. And so that segment would be considered an altitude. Notice again, that 90 degree spot is not in the middle of that side, and that's fine. But what is important is it starts from a vertex and it goes to a 90-degree angle. That's what makes an altitude. Let's see what happens if we draw that from another vertex in this triangle. Let's say the other corner, the other angle. Same thing, starts from a vertex and makes a 90-degree angle with the side of the triangle. And let's do one more from our last section, last vertex here. And same as before. Now, all three of those were inside the triangle. Let's see what happens when we get a right triangle. So this time, our triangle is right triangle. So there's our 90-degree box to show that this is a right triangle. So let's say that we start and draw this time from this top corner. Well, here's what it means by your altitudes could be on the side. Because if I follow along that edge, my altitude is the exact same as one of the sides of the triangle. It still connects from a vertex to a right angle. So that still works. Let's see what happens if we go from a different corner. Same thing will happen if I start at the bottom right corner. I have to follow the side of the triangle in order to make the altitude for that vertex. Sorry, I'm having technical difficulties here. What is it doing? Okay, and if I do it from the vertex where the 90 degrees is already at, that one actually goes inside the triangle. Okay, so that's what it means by sometimes they could be on a side. So I'm just going to redraw this one, and there's my altitude. Now, obtuse triangles are a little different. So if I was to draw my altitude from this bottom right vertex, yes, it's going to be inside the triangle. But when I go to the other two vertices, that's where we have something a little bit different. Because no matter, let's say I start from this top one, no matter where I try to draw, I can't make a 90-degree angle inside the triangle. So this is where we get the idea of sometimes they can be outside. So we have what's called down here at the bottom, that little dashed section is called an auxiliary side. Sometimes when the sides of our figures are not long enough, we have to extend it by using the dashed parts there that really just says, if this line were to keep going, this is where it would be, even though it's not a part of the actual side of the triangle. So I can use that auxiliary side to show my altitude. Okay, now if I was to do the same thing from my other vertex in the other corner, I would then have to extend out the opposite side, and it could connect out here. So sometimes they end up being outside. Okay. Now, just like our other figures, we had 3 of each kind of special segment. We do here as well for altitudes, and we call this the orthocenter, which is the point of concurrency for the altitudes. Okay, so the orthocenter is with the altitudes. And like before, it's where all 3 altitudes connect. So if I go back to this first triangle, remember we said this one was acute. Let me get our 3 altitudes back up here. So there's one. That one's not quite perpendicular. Let me try that again. There we go. It's a little better. And then from our top. And there is my orthocenter where all 3 of them come together. And again, notice when all 3 altitudes are inside the triangle, the orthocenter is inside the triangle. So again, this was your acute triangle with an inside orthocenter. When we have the right triangle, okay, let's get all 3 altitudes up. So there's the first one, our second one, and then the third one, and they actually meet at the right angle. Okay, so for a right triangle, they meet at the right angle. And then our obtuse. So let's get our altitudes up here. And again, I would need to extend this other side out. Now, it looks right now like these do not intersect, but if those were to keep going, again, create some auxiliary pieces here. They would, in fact, intersect just way outside the triangle. And again, there's nothing wrong with that. What's happening is that as that one angle is getting bigger, that orthocenter is moving farther and farther away outside of the triangle. But again, if it's obtuse, the orthocenter is outside. If it's a right triangle, the orthocenter is at the right angle. And if it's acute, they're all inside. All right, so let's take a look at our one example that we've got for this time. in triangle JLP, the measure of angle JMP, so let's find that guy, J connecting to M, connecting to P. So we're looking at this angle. Oops, sorry, I didn't mean to make a 90 out of habit. There we go. The measure of this angle is 3x minus 6. Find the value of x that makes Jm an altitude. All right, so again, if Jm is supposed to be an altitude, it should start at a vertex and connect to a 90. So we are going to have to set this equal to 90 if it's going to be an altitude. So 3x minus 6 equals to 90. Let's solve this out. So we can add that 6 back to both sides of our equation. So 3x is equal to 96. Now we can divide out the 3. And my x is equal to 32. And there is our final. So again, if this was going to be an altitude at the side of the triangle, it has to be 90. So that's why we set our equation equal to 90. All right. Okay, guys, I hope you enjoyed learning a little bit about the altitudes in triangles. Please don't hesitate to reach out to me if you have any questions at all. Have a great day, guys. Bye.